In this lecture, I'll give an introduction to statistics. Let me start off by dividing statistics into two sections. One I will call number crunching, and there's an R on the end of it, which is sort of a derogatory term for all the calculations, sophisticated calculations that we do in statistics. The Mendenhall textbook for this course is devoted pretty much to number crunching. That is why the material that I discuss in this chapter, he only gives a few pages in his chapter 1. The other section, shall we say, of statistics could be called something like sophistication or judgment. Okay, this is what I would like to begin to develop in you in this chapter. This other book that I have listed here, Statistics by Friedman, is devoted almost entirely to developing this kind of sophistication. By sophistication, I mean the discernment to look at a study or look at numbers and say, this is valid, this doesn't seem valid. All your calculations can be correct, but it could still be an invalid study. I think that if the only thing you get out of this class is that a sort of a sophistication about statistics, the ability to make some kind of judgment, to have some discernment about what is being presented, I think that would be absolutely wonderful. It's like if someone says to you, or when you hear statistics say, then you should sort of, kind of go inside of yourself and kind of chuckle and say, well, let's see about that. And you'll know what to look for to decide if indeed the statement statistics say or the statement after that has any validity at all. Statistics itself has several divisions. Two of them are based on how the information is processed, and they are called descriptive statistics. We have a chapter on that in this course and in the book. That's some of the real basic number crunching of statistics. And the other are called inferential statistics, and that's a group of methods for evaluating hypotheses, trying to decide probabilities. The inferential statistics makes use of the descriptive. The other division in science is based on how information is obtained, and there's two ways to do it. One is through observational studies, let's just say studies instead of statistics, observational studies, and the other is designed experiments. This is where your sophistication comes in. It's crucial to distinguish between an observational study and a designed experiment. Let's start first with a short description of the descriptive statistics and the inferential statistics. For descriptive statistics, there are a group of methods for organizing and summarizing the information. Basically, you're going to graph it, you're going to find out what the averages are, the mean, median, and mode. You're going to look at how the data values are dispersed about the mean by using standard deviation and variance. Those all come under the heading of descriptive statistics. Inferential statistics tries to draw conclusions from the data values. So you have information that you've obtained, now you want to draw a conclusion. You want to ask, is this the average value for the whole population? How do we think this vote is going to go? Those are the sort of conclusions you want to draw, and those are drawn through inferential statistics. Of course, before you try to draw some conclusions, you first have to organize the data, and that is why inferential statistics makes use of the tools of descriptive statistics. Now we come to the heading or the topic of a designed experiment. In a designed experiment, one starts with a population. It could be a population of people or plants or animals or anything you're trying to look at. Usually that population has some sort of a continuity to it, I'll say normally distributed. From that population, you extract a representative sample. You can't ask everybody, well, if you asked everybody in the country how they were going to vote, then you just pretty much had an election. But instead you draw a sample of people to ask, to make inquiries of. That sample has to represent the population. If the population is 75% male and 25% female, the sample that you draw should also be 75% male and 25% female. So it represents the population. That means you have to think for a long time about what the population is, what are its attributes, what are its variables, in order to characterize it. And then you have to draw that sample. There's various ways of doing this in design experiments. Once you have this representative sample that you've created, you now take that sample and you divide it up into groups. All right, so you're going to divide it into a control group, that's over here, and you divide it into some kind of treatment groups. Maybe there's several treatment groups. For example, you might be testing some kind of medicine. So you would have this representative sample of the people who are going to be subjected to this medicine. You would get that sample of those people, and then you would divide them into a control group. That group you don't give anything to. Then you would have maybe 3 or 4 treatment groups. These people, first group gets half a pill, the second group gets 2 pills, the third group gets 5 pills a day. Okay, that's the different treatments that you assign to those groups. Now each one of those groups has to be another little microcosm of the representative sample. For example, if you drew that representative sample of 75% male, 25% female, and you put all the females in the control group, your results aren't going to be valid. Okay. Now how do you get them from representative down to these control and treatment groups? You have to make sure that you don't add any bias. Okay, and there's various ways of eliminating that. Basically, we say that they are randomly assigned into the control and treatment groups. So a person might say, I want to be in the group that gets 5 pills a day. No, you don't get to pick it. You're going to go into the group that you're assigned to. Okay, or somebody might say, oh, I don't want to put this particular person into that. I'll want them over in controls. No, even the experimenter doesn't get to assign the people. They have to be done by some kind of random process. Now, by doing a designed experiment, you can possibly determine causation. And by causation, it could come under many categories. You might be trying to determine if that pill causes a certain side effect, or if it has a certain effect on the person. You're trying to determine causation through the use of a designed experiment. Notice you're working with a small group of people, pretty much in an artificial situation. Now let's look at an observational study. An observational study can only reveal association. It cannot reveal causation. In an observational study, data is gathered from something that's happening now, or perhaps something that happened in the past. That's called a retrospective study. There is no random assignments to control or treatment groups. There usually is a control group and a treatment group in an observational study. The treatment group is usually the one with the condition or the disease. The control group is the one without. For example, if you're studying the effects of smoking in an observational study, right, the treatment group would be the people who smoke. The control group would be the people who don't smoke. So there are treatment and control groups. If there is a voluntary situation where people volunteer for a medical test or volunteer for something, the treatment group are the volunteers, the control group are those who do not volunteer. You can see that those are not necessarily matched. In fact, they're not matched right at the start. They already have a big difference between them. Now, why would anyone do an observational study? Well, first of all, it can be done in a natural setting. And there are some things that experiments can't do because it would be unethical or just plain bad. For example, you can't have, it's really hard to do experiments on children. You have to be very careful on doing an experiment on children. You can't do a designed experiment on suicide, something serious like that, or some horrible crime like murder. You can't assign certain people to be murdered and certain people not to be and see the effect on their family, for example. You can't do that. So you're looking at observational studies in that sort of situation. Also, there are times when variables cannot be manipulated. For example, if you're trying to study whales, you don't have little tanks or big tanks to put some whales and put some whales over here. I mean, that's not going to work. You simply can't manipulate whales like that. So there are real good reasons for observational studies. But the bottom line is they can reveal only association, not cause and effect. Now, if you can keep those two in mind, when someone says X is caused by Y, and they quote an observational study, you should be able to say, no, all you've shown is association between variables X and Y. You have not shown causation. Okay, but then even observational studies and designed experiments can have problems with them. And I want to give some examples for those. So here's the important concepts. Observational studies can reveal only association. Association might point to cause and effect, but it does not determine it. And there's another topic, and that's coincidence or correlation does not imply causality, because two things happen at the same time does not mean one causes the other. And the classic examples are, if it seems to, or if it does, rain every time I wash my car, washing my car does not make it rain. If the dog is present in the house when the homicide occurred, did not mean the dog created the murder. Okay, so you have to remember that. But sometimes when things seem to be going in the same direction, there's this idea of, oh my gosh, I've discovered causality, and I haven't. Now, one of the failings of both observational studies and sometimes designed experiments is a failure to take into account confounding variables. A confounding variable is some variable associated with a situation that you didn't control, you didn't take into effect, and yet determines or has a big influence on the outcome of the experiment. The classic example is testing a diet pill and not taking into account exercise. So you might have done your whole experiment, you've got your control group and that's not giving the pill, you've got another group that's given half a pill, the other group's given 3 pills. Okay, well then your control group here suddenly gets interested in Zumba. Okay, now your whole results are off, right? Because you did not take into account exercise. Okay, that other example was sort of lighthearted, but here's another one. Of course, I made that one up, but now this is some true data, and you can find this information on this one and other examples in Friedman's books on that, Statistics by Friedman. Okay, this was an observational study done at Johns Hopkins, which of course is a world-class hospital and research institute. And the question being examined is, does ultrasound of babies lead to low birth weight? They did an observational study, and they did a fairly good one. They tried to take into account many confounding variables. Here's the ones they took into account. Okay, race, whether the person was a public patient or a private practice patient, the smoking, alcohol history of the mother, the gestational age at delivery, was this premature delivery or was it term or post-term? What's the method of delivery, right? Did the mother have a history of prior miscarriages? Was amniocentesis or fetal monitoring performed? What's the educational level of the mother? And what was the mother's weight and what was her weight gain? Okay, so they've got all kinds of variables controlled. They did this observational study, and the observational study showed that there seemed to be an association or correlation between low birth rate and the number of ultrasound exams that have been given. So now, from what you've known so far, did ultrasound cause low birth weight? Can you say that ultrasound causes low birth rate? And the answer is no. This was only an observational study. It shows association. We aren't even really sure of the association, but it will only show association. Even if it were true that ultrasound caused low birth weight for some reason, this study cannot be used as evidence because it is only an observational study. Now there's a little monkey wrench in the works here, because there was another confounding variable that this study did not take into account. And I said previously, these confounding variables are the plague of observational studies. There's a real tendency to miss them in an observational study. In this case, here's what they missed. When there was a problem with the pregnancy, the the OBs ordered more ultrasounds. So a person who had a problem in their pregnancy ended up getting more ultrasound examinations. So there already was a problem, and so the birth weight might have nothing to do with ultrasounds. Later on, and this is reported, you can get the references for that, or I can give them to you if you're interested. There was another designed experiment. So this is one with control groups and random assignment to treatment and control. They tried to look at and examine this situation about this association between ultrasound and lower birth weight, and they found it was protective. They found out, so in this case, for a designed experiment, the control group and the group that were getting ultrasounds had to have the same medical history, so that you couldn't have, if you look back at that observational study, the control group would be people who never got ultrasounds, possibly because they never had a problem with their pregnancy at all, or maybe they only had one. And the group that had many, that would be your treatment group, actually had problems in the pregnancy. So in the design experiment, all of the groups, the control group and the treatment group, would both have to have similar medical history. They would have to have similar problems with the pregnancy. And the result of that experiment showed that ultrasound was protective. The group that had the more ultrasound examinations ended up with higher birth weights than the control group. But again, in this case, we're comparing apples and apples, where in the observational study it was more apples and oranges. Now let's look at a problem that can happen with a designed, or rather mal-designed, experiment, and that is the use of what are called historic or historical controls. All right. With historic controls, the experiment is set up so that certain people undergo a procedure, and their results or their outcome is compared to people in the past who did not undergo the procedure. Okay, that's different from contemporaneous controls, in which you have the group right in front of you and you randomly assign people to control versus treatment. The problem with historic controls is the makeup of that group. You're looking at old patient records, or you're looking at some old data. One problem is that the people in that group may have had exactly the same disease. We're thinking in terms of medical right now, same disease or same condition as the treatment group, and that may be very true. However, maybe they had something else and they were not candidates for the treatment or candidates for the surgery. And here's an interesting example. Again, this is from the Friedman's book, and there are references there to the publications if you want to look these up. In this, the topic is CABG. That's coronary artery bypass grafting. That's operation they do when you don't have sufficient blood supply to your heart, and they harvest a vessel from somewhere else, leg or arm or somewhere, and they going to make a little jumper there, and they bypass the blocked artery and bring blood supply to the heart. So the question is, what is the benefit of CABG? And in this case, they looked at the 3-year survival rate with surgery and without surgery. So let's look at the one with historic controls. So the study with historic controls, they looked at people with similar heart disease in the past and compared them to people in the present in terms of the experiment, who underwent CABG or didn't. Okay, well, underwent CABG, right. So the 3-year survival without surgery, this would be the controls. These are people historically had a 71.1% survival rate 3 years after the start of this, but without surgery. Okay, the 3-year survival with surgery was 90.9%, and that looks like it's a very good benefit to having CABG. All right. Okay, let's look over here at the designed experiment. In this case, there were contemporaneous controls. People were randomly assigned to both groups, and look at the difference. The 3-year survival rate without surgery, 83%. 3-year survival rate with surgery, 87%, almost no difference. Well, there is certain difference, but it's certainly not as great as what is seen over here with historic controls. So this shows you that the difference in outcome that can be achieved, and probably the reason is that the historic controls were not candidates for the surgery. If you have some other things wrong with you and you wouldn't have get through the surgery, of course they don't take you to the operating room. And those were some of the people in the historic controls. Now the interesting thing, which is sort of almost a sadness, is look at the number of people in this study. I mean, this is not a small study using historic controls, and it's not a valid method. So you kind of wonder, would have been a lot of work. And there were 9 of these studies altogether. For the design experiments, there were actually 6 experiments, and they had many patients over there too. Almost 9,000, over 9,000 people in the designed experiment. The other topic, or sort of fallacy I want to talk a little bit about, is that coincidence is not causality. And here's another example from medicine. Just looking at the data in the past when we have polio epidemics, the children with the higher risk, the children more likely to get polio, were those that came from wealthier families. Okay, so now you have an association between money and polio. Does money cause polio? Well, obviously not. And that is, you can think of that as a classic example of coincidence and not leading to or not determining causality. Another one that's used as an example are the ancient Chinese firing off fireworks during an eclipse. The idea being that the eclipse of the moon or the sun, the sun or the moon was eclipsed because a dragon or a dragon was blocking it. So when you fire off the fireworks, well, that scares the dragon away and the sun or the moon show up again. Obviously, that's quite coincidental, and surely shooting off the fireworks does not end the eclipse. So here's a small summary. The homework for chapter 1, I have some different scenarios in there, and you can look at those and decide if they're experimental studies, or experimental design experiments, or observational studies, and whether you can draw conclusions for them or what conclusions you can draw from them. Basically, an observational study does not create representative samples from population. It doesn't assign samples randomly to control groups or treatment groups. I think there's too much control in that statement there. It can show association only, not cause and effect, and it is plagued by confounding variables. Observational studies are done for ethical reasons or for environmentally, in a sense, like it's a situationally uncontrollable variables or uncontrollable situations. The designed experiment can hope to show cause and effect. There still may be design problems, so even if it's a designed experiment and you really want to test its validity or examine its validity, you need to see how that experiment was conducted, how did they get their samples, who did they use for controls, and it also can be plagued by confounding variables, and the use of historic variables makes the results invalid.